Good morning, dear student. In today's lecture, we will discuss the second important type of reaction of olefins, that is oxidation reaction. So in previous lecture, we will discuss different types of CC coupling reaction. So in today's lecture, we will discuss the oxidation regarding to the oxidation of olefins. So in this lecture, we will discuss the very common example of the oxidation of alkenes, that is carbon-carbon double bond, and the conversion of alkenes into aldehyde. That is, we are very much familiar with this process. It is known as wacker process. So, what is wacker process? So, in this wacker process, the alkene is converted into aldehyde. The alkene it is converted into aldehyde with the help of PD second PDCl2 as a catalyst, active catalyst in presence of water, and Cl4 2 minus as a co-catalyst. So if you consider this Wacker process, the active catalyst for this Wacker process is PD second, and for this when alkene is converted into aldehyde, the PD second get reduced to PD0 oxidation state. That is, whenever one molecule of alkene is converted into aldehyde, the PD second is converted into PD0 oxidation state, and therefore for again convert this PD0 into PD second, we required another catalyst. That is, in this process, for the conversion of PD0 again into PD second, we required a catalyst. It is known as a co-catalyst, and the co-catalyst is copper second. That is, so in this process, copper generally it is in +2 oxidation state. It is used as a co-catalyst which convert this palladium in 0 oxidation state into palladium in +2 oxidation state. So as the copper second, it is act as an oxidizing agent. It will oxidize the PD0 into PD second, and itself get reduced into copper first. That is conversion of copper second into copper first. So it undergo reduction reaction, and the palladium get oxidized to PD0 to PD second. And we know that this PD second is a very active catalyst. So it is an active form for this Wacker process, that is conversion of alkenes to aldehyde. Again, if you consider when this copper second is converted into copper first, again we know that for conversion of PD0 to PD second, we require copper second. So whenever PD is converted into PD second, the copper second is converted into copper first, and for the conversion of copper first into again copper second, we required acidic medium and O2, or 1/2 molecule of O2. So for the conversion of copper first into again copper second, for the conversion of PD0 into PD second, we required acid and 1/2 O2 molecule. So with the help of this acid and 1/2 O2 molecule, we convert this copper first again into copper second, and this copper second it is used for the conversion of PD0 to PD second. So because in this process, in this Wacker process, the PD second is an active catalyst. So if you consider the catalytic cycle for this oxidation of olefins, so catalytic cycle for this Wacker process, so generally the catalyst which is used in this Wacker process is PD second. So generally PDCl4 2 minus species, that is a square planar species, that is PD, and it is attached to palladium. It is attached to 4 ligands, chlorine ligands, and the complex having -2 charge. So it is an 16 electron species. It is the active form in which the palladium is in +2 oxidation state. It is the active species. It undergo reaction with olefins. So this PDCl4 we know that this 4D and 5D metal atom generally form square planar complexes, and therefore for further reaction with alkenes, there is a replacement of ligand from this PDCl42 minus. So it does not form, no doubt it is, if you consider it is coordinatively saturated, means it will form only complex up to coordination number 4. So for further addition of any other ligands, it does not forms a higher coordination number species, such as coordination number 5, coordination number 6. So in this case, whenever any ligands when attach, or it will react with this PDCl42 minus, it will undergo dissociation of one ligand, and then after dissociation the other ligands will binds with this PD metal atom. So for this, if you consider the first reaction of this catalytic cycle, that is the PD second PDCl42 minus undergo olefin uptake, that is reaction with olefins, carbon carbon double bond, and we know that the carbon carbon double bond, its hapticity is 2, and therefore in this case there is a removal of Cl minus, because we know that the Cl is one electron donor and the Cl minus, so if you consider the chlorine, it's one electron donor and it have a negative charge, therefore it contribute 2 electrons. So when alkene is bind with palladium, then there is a removal of Cl minus, because Cl minus, it is a 2 electron donor. So what you get after dissociation of this Cl minus and reaction of this PDCl42 minus with olefins, we get PD, which is attached to 3 chlorine atom, which is attached to one alkenes carbon carbon double bond, and the complex having negative charge. So if you consider in this case, again the complex is 16 electron species after dissociation of Cl minus. Again if you count the electrons, that is PD contribute 10 electrons, these 3 chlorine contribute 3 electrons, one negative charge contribute 1 electron, so total 14, and this alkene contribute 2 electrons, so total 16 electron species. This is the 16 electron species. So dissociation of Cl minus and addition of substitution of Cl minus by the olefins, that is carbon carbon double bond. So the electron count does not change in the first step. The next step again is the replacement of another chlorine ligand by the water molecule. So replacement of another Cl ligand by the water molecule. So if you consider this, there is a 3 chlorine atom which is attached to the palladium. The 2 chlorines are cis to this carbon carbon double bond, that is alkene, which is attached to metal atom, and 1 chlorine is trans to this carbon carbon double bond, that is it is trans to alkene. So which chlorine is removed, get substituted by water molecule. So if you consider, so we are very much familiar with the trans effect. So what is trans effect? So if you consider with respect to this 3 chlorine atom, this alkene has very strong trans effect, and therefore whenever a incoming ligand it is attached to this metal atom, it must be trans to this alkenes. So the ligand which is trans to this alkene, it is replaced by the water molecule. So after replacement of water molecule, again there is a removal of Cl minus ion. Again there is a removal of Cl minus ion. So 2 electron species, Cl minus ion is 2 electron species. So what you get after removal of this Cl minus, the chlorine is replaced by the water molecule, and again we get a species, that is PD. It contains 2 chlorine, 1 alkene, and 1 water molecule. Again if you count the electron, in this case the PD contribute 10, this 2 chlorine contribute 2 electrons, so total 12. This alkene contribute 2, so total 14, and this water molecule, it is the chlorine is replaced, the Cl minus is replaced by water molecule, therefore it is 2 electron donor, and therefore the species is 16 electron species, and it does not have any negative charge. So you should keep in mind. So in this structure, the water molecule, it is a 16 electron species. After that, we know that the coordinated alkene is electrophilic in nature, and there is a nucleophilic attack by the water molecule on this alkene. So we get by nucleophilic attack. After nucleophilic attack, we know that whenever a nucleophile is attacked on coordinated alkenes, the hapticity of the alkene is decreases by 1 unit, and again we get the PD, which is attached to 2 chlorine atom, 1 water molecule, and the hapticity 2 is converted into hapticity 1, that is CS2, CS2, and OH. So the palladium, it is attached to only 1 carbon atom, and again if you count this electron, then the PD contribute 10, this 2 chlorine 12, water molecule 2, then it is 14, this CS2 CS2OH contribute 1 15, and for 16 electron the complex must have a negative charge. So after nucleophilic attack, the hapticity of the alkene is decreases by 1 unit, and the complex must have a negative charge. So it is a 16 electron species. So if you consider the ligand which is attached to this palladium, that is CS2 CS2OH, it must it having a alpha hydrogen, and therefore there is a chance of beta hydrogen elimination reaction. So for beta hydrogen elimination to occur, there is a removal of this water molecule. So we know that. So for this catalytic cycle, the coordination number of this palladium is 4. It does not change, and therefore for beta hydrogen elimination reaction to occur, we must remove this water molecule, and this water molecule, it is replaced by the hydrogen, that is the beta hydrogen elimination. That is the beta hydrogen, it is shift from carbon number 2 to this palladium, and what happened due to this beta hydrogen elimination, the hapticity again it is increases by 1 unit, that is the hapticity 1, it is converted into hapticity 2, and there is a replacement of 1 water molecule, because we required a coordination number 4 to maintain the catalytic cycle, or to maintain the we can say that to maintain the stability of the complex. That is in this case again the PD, it is attached to 2 chlorine atom. After that it is attached to the hydrogen, and it is attached to carbon carbon double bond. So because after beta hydrogen elimination, the hapticity 1 again it is converted into hapticity 2. So after that there is a 1-1 insertion reaction, or we can say that there is a 1-1 insertion reaction, that is the hydrogen, it is shift, so it is a sigma donor ligand, and it is shift from this metal atom to this carbon carbon double bond, and in that case what happen, the carbon number second, it will forms the bond with this palladium, because if you consider before this insertion reaction, both the carbon atoms are attached to this palladium, but after insertion, so if you consider after insertion, the hydrogen, it is attached to this, hydrogen is transferred from this palladium to this carbon atom, and therefore again the hapticity is decreases by 1 unit. So what you get after insertion reaction, we get the palladium which is attached to 2 chlorine atom, then the carbon, single carbon is attached, the carbon having one OH group which is attached, one OH group, one methyl group, and the alkene, it is converted. After the alkene is converted into hepticity 1, and therefore after transfer of this hydrogen, then it is converted into a methyl group. Therefore the carbon must be attached to this OH group, one hydrogen and one methyl group. Again, if you count the electron, then it is PD 10, this 2 chlorine contribute to 12, and this carbon it is contribute 1 electron, so total 14. So if you consider this is if you consider this species, that is PD Cl2 CHOH, so it contribute, PD contribute 10, this chlorine contribute 2, so 12, this contribute uh, 13, this carbon contribute 1 electron, that is 13, and 1 negative charge, so it is a 14 electron species. And after that uh, the species which is formed, after that it undergo H minus, that is removal of not H minus, removal of H plus, so removal of H minus to gives the aldehyde. So we get the final product with PDCl2 is the active catalyst. So this is the catalytic cycle. So if you consider again the last step, that is after insertion reaction, the hepticity is decreases by 1 unit, and the complex, that is PDCl2H carbon carbon double bond and negative charge, it is converted into PD, which is attached to 2 chlorine atom, and then it is attached to the carbon having one OH group, one hydrogen and one CH3, and for 16 electrons. So if you count again the electron, this PD contribute 10, this chlorine contribute 2, so total 12, this contribute this C carbon which is attached to the palladium contribute 1 electron, that is 14, and for 16 electron species the complex must having a -2 charge, so -2 charge should be there for 16 electron. Then after with the removal of H plus, the species undergo we can say that the breakage of OH bond, and we get the aldehyde. When this hydrogen it is shift, so if you consider this OH, the bond between oxygen and hydrogen is break, then it is converted into C double bond O, so we get C double bond O, that is carbon oxygen double bond, and this PDCl2 bond get break, and we get a final product, that is aldehyde. And again this PDCl2 react with further Cl minus ion, so this PDCl2, no doubt it is in +2 oxidation state, so it is the active catalyst. So the regeneration of this active catalyst, and we get the final product, that is your aldehyde. So this is regarding to the oxidation of olefins. So we are very much familiar with this wacker process, so you should remember the active catalyst is PD second. The conversion of alkenes into aldehyde, whenever there is a conversion of alkenes into aldehyde, the PD is converted into PD second. And to convert again this PD second, PD 0 into PD second, we required a second co-catalyst, that is copper second. Generally it is CuCl42 minus, it is used as a co-catalyst in this wacker process. It convert this PD 0 into PD second, and itself get reduced from copper second to copper first. Again we required this copper second for the conversion of PD 0 to PD second. For the catalytic conversion of copper first into copper second, we required acidic medium and 1/2 photo molecule to convert the, copper first into copper second, which is very useful for conversion of PD 0 into PD second, because PD second it is your active catalyst. So this is all about the oxidation of olefins, that is with the help of that is the important example for this oxidation of olefin, that is wacker process. We are very much familiar. So again the catalytic cycle, the first step is the 16 electron species PDCl42 minus is active species. It undergo substitution reaction with olefins, a replacement of Cl- by the